Because chemistry is a quantitative science, Chapter 2 is devoted to a math review and a discussion of measurements and precision in measurements. The opening story is about global warming over the last 100 years, and this image shows a 0.6 degrees Celsius increase in temperature over that large time window of 100 years. 0.6 conveys information to us. It's about a degree Celsius. It doesn't seem very large, but it tells us an extra layer of information because scientists use digits to express the precision of the instruments. And this set of instruments that have determined this are good to the tenths of degrees Celsius. Just keep this in mind as we go through first the math review, that science is about measurement, and there's extra layers of meaning to the measured quantities, and that's known as significant figures. Let's first review scientific notation. We have the base, which is the format of one-digit decimal, the other significant figures, times 10 to the n power. That's our usual format. If we have a positive n, positive exponent, that's a big number, and if we have a negative n, that's a little number. So if we have 10 to the third, that means 10 times itself 3 times, which is 1,000. But if we have 10 to the minus 3, that's 1 over 1,000, or 0.001, left movement of the decimal. So let's practice converting numbers to scientific notation. If you have the number 5983, how do you write that in scientific notation? We move left 3 to get the one-digit decimal, the rest of the numbers, times 10 to what power? What power would I say? Did you say 3? Let's look at the next example. If you have 0.00034, how would you write this in proper scientific notation? We get one digit, the rest of the number, times 10 to the what? We moved 4 times. To go left. Let's see if we agree with that. Here are your answers. One more try. The radius of a carbon atom is approximately, this is a lot of zeros, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 zeros, 70. How would you write that in scientific notation? We say you're allowed one digit, the rest of the number. We'll discuss in a moment. That's significant. 0.0 times 10 to what power? We had 10 zeros, but we have an extra move. Minus 11? Is that what you would say? That's the answer. So now let's go a little more detail into significant figures. On the left, you have counting numbers, such as 7 pennies. That's not what we're talking about with significant figures. We call that a pure number. Everything significant, the 7, has no limit of significant figures. But on the right, we have a 10-gram gold bar. And the number of significant figures would depend on which balance you measured the gold bar on. If you measured it on a fine balance, you could potentially read 10.000 grams. Or if you had a crude balance, maybe the best you can do is 10 grams. This is a measured quantity, and the number of significant figures reflects how precise the measuring device was that you used to measure it. This is a balance measuring some blue stuff. It's copper sulfate. The balance is a small picture. This is 0 and 1, and we're past 1 slightly. The balance gives us the 1 gram mark for sure. That's the certain. And then we can see it's a little beyond, and on its way to the 2 line, but less than halfway. In fact, in our mind's eye, we separate in 10 spacings, and we would say this is 1.2 grams as our reading, the one certain digit and the one estimated. Here's another balance. This scale is to the tenths of grams. We put this pistachio on here. We can see we're past the 1, we're past the 1.2. In our mind's eye, we separate 10 spacings between the 0.2 and the 0.3, and we would say 1.26 grams. 2 certain, 1 estimated, for a total of 3 significant figures. That's the most precise reading that we can take from this balance. Alright, here is a scale. This happens to be in pounds. It's someone's weight, probably. What would you say is this person's weight? We see this is the 150 line. This is the 145 line. We have cleared 147. We're in between 147 and 148. We're more than halfway past. We could say that this is 147.7 pounds. Now we have a bunch of rules. This is if you're just looking at a number, and this is a rule list that you should read, but it's best learned through practice. So you could pause this and read this. I'm going to go on and apply these rules. How many significant figures are in these values? Let's say these are measured quantities. They'd be grams or meters or milliliters. 0.0035 has how many significant figures? We would say the front zeros are just placeholders and have no significance, but 35 does have significance. We say this has 2 sig figs. The number 1.080, sandwich zeros always count. Trailing zeros after the decimal count. It only was placed there to show that the balance or device measured to the thousandths position. So we would see this as 4 sig figs. They all count. The next one's the easiest one. They all count. All non-zero digits count. The next is 2.9 times 10 to the 5th. Scientific notation makes it easy. Everything in the base counts, so we say 2 sig figs. Next, 1 dozen is counting, so it's infinite. And the next one, 100.00. Well, this is sort of like our bank balance. If you had $100.00, you know you would have no cents. They all count. Everything's significant. What if you had 100,000? That's very confusing measurement. Who knows how accurate or precise the measuring instrument was? Without a decimal point, we have to assume that's only 1 sig fig. Alright, now we want to address rounding. What if you have a measurement, such as these numbers on the left, and you don't get to keep all those digits? You have to reduce it down to 2, let's say. How would you round these numbers to 2 sig figs? If you had 4.35 and you had to limit it to 2, you kind of draw a line down 2 digits over and look to the right. If it's 5 or more, you round up. So you say 4.4. But if your number was 3002 and you get 2 sig figs, we, in our mind's eye, draw our line. Look to the right, it would not be rounded up. We would say 3000. But 3000 would only have 1 sig fig. So we must put it in scientific notation to be clear. We have 2 sig figs. Last example, if you have this number and you only get 2 sig figs, we know these trailing zeros are just placeholders. They don't count. We go 2 digits over, draw a line. Is it 5 or more? No. So this would have 2 sig figs as an answer. What if you're doing math? Let's first look at multiplication and division. you match the least number of significant figures in the original numbers. Here's an example. Let's say you are multiplying these three numbers. This one has 3 sig figs. This one has 5 sig figs. This one has 2 sig figs because this 0 counts. Your calculator gives this number, but you apply sig figs rules. You match the least. Because you only had 2 sig figs on this number, your answer is only allowed 2. When you, in your mind's eye, make a vertical line here and look to the right, you would not round up. It's 45. Let's take an example. What if you were dividing 5.892 by 6.10? Your calculator says this. What would you say? How many digits do you get to report? I hope you said this. You only get 3 because of this number, limiting it to 3. This was a rougher measurement. Therefore, our answer reflects that precision. You get 3 sig figs. Our calculator says this. We draw in our mind's eye a vertical here. We look to the right. We are going to round up, so we say 0.966. The addition and subtraction rule is slightly different. If we're adding and subtracting numbers, we match the number of decimal positions. This is an example. If you were adding these three numbers, because this number right here only goes to the hundredths position, our answer is limited to the hundredths position. So we would say 9.21 as a result. Here's a practice problem. If you were subtracting 3.965 from 4.8 and your calculator says this, what would you actually report? I hope you said 0.8, because you have to match only to the tenths based on this rougher measurement. If you have combinations of operations, you can pause this slide and read this, but the rule is basically apply sig fig rules along the way, but do not round until the finish. So in this mixed combination of math operations, we're taking a 3.489 and multiplying it by this difference. First we take the difference, we get a number 3.37, but we note we only get to go to the tenths position, and so a lot of people underline that number to say that that's significant. We then go on to finish the math, 3.489 times this. Then the multiplication rule says count sig figs in each of the numbers. 4, only 2. Therefore, my answer is reduced down to 2. I do so by rounding. I look to the right. I see it's above 5, so therefore the answer on this is 12. We're now done with 2.1 to 2.4. I know I moved very quickly through this material, so that's the luxury of videos. You can go back and watch it again. I want to finish with an interesting case in history, a tragedy. So this is the Mars Climate Orbiter. It crashed in 1999 based on, here's a news clip from the Washington Post. The Mars Climate Orbiter was lost in space because engineers failed to make simple conversion from English units to metric, an embarrassing lapse that sent the $125 million craft fatally close to the Martian surface. I think it's helpful to summarize sections 2.1 through 2.4 by applying to a laboratory experiment, just as you will need to apply this information to your laboratory experiments. So let's pretend that Zach, Charlie, and Phyllis are lab partners, and the first step of their experiment is to measure the masses of these three cylinders. And so Zach goes to a balance, and it measures this brown cylinder to have a mass of 2.14 grams. Charlie takes this blue cylinder to a different balance. He gets 4.2 grams. And Phyllis takes this tan cylinder over to the nicest balance in the room, and it gives lots of digits, 3.339 grams. And they need to get the average mass. The first thing I want to point out is there are multiple layers of meaning to these measured values. The 4.2 grams, that tells us that as far as value goes, this is the most massive cylinder. So the information of precision, here we go, value. We know that this is the most massive cylinder because it is the biggest number. The second factor is what we mentioned about number of digits, the whole idea for sig figs. Our most precise instruments give us more digits, and that talks about the precision of the measurement. So in science, we care about the precision of the reported measurement. And finally, the information of the units. And you need to get in the habit in this course to always put your numbers with units, and that makes sense. Then we can speak the same language. The final point is, if we were to get the average, we would sum these up and then divide by 3. If we sum them up, we know because of this guy right here, we only get 1 digit past the decimal. Then when we divide them, we are again limited by this guy, because only 2 sig figs. So our final average mass will only have 2 significant figures based on the low quality balance that Charlie used. So I hope that wraps up the ideas from this chapter, and we move on to talk about converting units.